In this video, I'd like to talk about a T-simulation program that I put together. Now, basically, we've run 1,000 subjects in 3 groups, so that's 3,000 subjects. This is an independent t-test. They're not matched. And I'll show you what I did. Each row here represents a simulated study. It has an N of 10 people in the group. In this first case, the mean was minus 0.023 and the standard deviation was 1.236. And then these are the individual 10 values. So the standard deviation comes from these 10 values, and the mean is the mean of these 10 values. Now, where did I get these numbers? These numbers, I used Excel's random function for normally distributed data. So if we go into data analysis, we can find a random number generator, and you can put down a number of variables, which I did 10 across, the number of random variables, which I did 1,000 down, and the distribution was normal. This is a random normal distribution with a mean of 0 and a standard deviation of 1. Now, I could have put anything in there, but this is a very general formula, and I told it to output here. So, unfortunately, unlike Excel's other functions, you put these numbers in, and they're a fixed number. They don't automatically give you a new random distribution each time. But we have exactly the same random distribution. Now, group 2, same way. Different random numbers because they were randomly generated. If we look here, this is the mean going down. You can see it's close to 0. This is the mean looking across the 10 values, which are each of these is the mean of each of the columns. Now, when we run a study, we only run one group we collect 10 observations on only one of each group. So we've basically essentially done this study 1,000 times, which you wouldn't do. You just do it once. But this is a simulation, and we're simulating it 1,000 times. Group 3, same thing. Everybody's generated with a mean of 0 and a standard deviation of 1. Now, when we come to this spreadsheet, we're going to change our data. We're going to use the data from group 1, but we're going to compute a z-score. So notice this says B10, which this is, B5, which this is B5 and it's 16. And so it's the value from our z-score, which was minus 0.023. Now, this has a mean of 0 and a standard deviation of 1, generally speaking, approximately. You can see it kind of came out that, but it's not exact because it's a sample. But it came out, and so a z-score is calculated by this is a value of x times the standard deviation plus the mean. The mean is 0, the standard deviation is 1. So, we can change that. So what we've done here is we've said, okay, I'm going to adjust this number by multiplying it times B5. So I'm taking that minus 0.23, I'm multiplying it times B5, which is the standard deviation of 16, and I'm adding a mean of 100. So I'm doing a linear transformation from a random number that has a mean of 0 and a standard deviation of 1. I'm transforming it to a new set of data that has a mean of 100 and a standard deviation of 16. I'm just doing a linear transformation, moving the mean from 0 to 100, moving the standard deviation from 1 to 16, and then I'm taking the portion, I'm taking the standard from the random sample, the minus 0.2, multiplying it times 16 and adding it to 100 because it's minus 0.2, it's subtracting a little bit. So our new mean, instead of having a mean of 100, now has a mean, or instead of having a mean of 0, now has a mean of 100. All right. Now, I did that for group 1 and group 2. Same thing. So I now have, when I'm running my test, before, I was comparing two groups with a mean of 0 in this group, or with an underline, mean of minus 0.023, and comparing it to a group with the sample mean of minus 365. I just do this to give it, this allows me to test a null hypothesis, where the underlying means are exactly the same, 100 and 100. Now, in group 3 here, I've got the same thing where the underlying random variables all have means of zeros and standard deviation of 1. But here, instead of multiplying times 100, I'm multiplying times 120. So I'm actually getting, I'm getting a difference between my means. Instead of 0, like in these first two, it's the difference between 120 and 100. This is the underlying one. Now you'll notice that even though the underlying mean is 120, the actual value is 124, means 100, the actual value 94. And so we get all these different numbers because this is a sample. It's not the true population mean. Now it comes out pretty close, but it is different. So we're going to start off, well, and then, so we calculate this mean. The standard deviation is taking, again, it's just the same thing. We take the minus, well, we take the, let's see, it's the C10, which is the standard deviation so we randomly create these 10 numbers from a random distribution, each one mean of 0, standard deviation 1. We get all these samples and we come up with a mean of minus 0.023 instead of the underlying mean of 0, but it's a sample. And instead of exactly a standard deviation of 1, our estimate of the standard deviation is 1.236. So then that standard deviation is multiplied times 16 and we get 19.8. It's a little bigger. It was 1.26, so it's a little bigger than 16. And we do that all the way across. Then we compute our standard error, which is the standard deviation divided by the square root of n. We calculate the confidence interval. It's the mean minus the t-value, which is t inverse times, given a two-tailed t-test with a p of 0.05, times the degrees of freedom, which are C8, 10 minus 1, or 9. And we get 85 to 113. So that's our confidence interval. Now I've calculated a 95% confidence interval. And in this one, I'm asking, does the confidence interval include 100? So, in other words, a confidence interval, if you do it a bunch of times in the long run, 95% of the time, it should include the confidence interval, or the true mean of 100. So the true mean is 100. And we got 85 to 113. You can see that actually matches. But if you come down here, occasionally you'll find a 0, which means the confidence interval was 78 to 97. So that did not overlap 100. So we had a few cases where the 95% confidence interval didn't overlap 100. Now I added up all these ones and I got 961. That meant, now I kind of expected, if this was a perfect world, there would be 950, because that's 95% of 1,000. So the confidence interval actually covered a few more than I would have expected. All right. I also calculated 84% confidence intervals because of our Goldilocks rule that we'll address in a minute. I did the same thing with mean 2 and mean 3. Notice mean 2 hit 95% right on the nose for the confidence interval, and the mean 3 came pretty darn close, 949. That means that, for example, this guy, 105 and 119 did not overlap 120. So remember, we're calculating a different confidence interval every time based on the sample. And the idea is that 95% of the time, this calculated confidence interval from the sample will overlap the true mean of 120. All right, now let's look at our t-test. Now, this is comparing group 1 and 2. And the difference is minus 5.5. So we take our sample, we look at 99.6 minus 94.2. Remember, the t-test is the mean of x1 minus the mean of x2 over the standard error, the pooled standard error of the difference, which is right there. This little mu minus mu, that's the underlying population mean. We're testing the null hypothesis, so we are testing the population mean of 0 minus 0, or 0. And since that's 0, and 0 taken from this value doesn't change anything. So we just have mean of x1 minus mean of x2 over the standard error of the difference. So if we take 99.6 minus 94.2, we get the difference of minus 5.5. Then this is the computed standard error. It's the square root of the two standard errors added to each other. So it's this one plus this one, each of them squared, and then the square root of that. And so when we divide the difference, you divide the difference minus 5.5 divided by 7.3, you get a t of minus 0.8, and the p is 0.463. Now that p-value means that the probability of getting a t of this value or greater is 4.63. Actually, this isn't quite right because that's a negative value, and it's really 1 minus 0.463, but we'll just kind of ignore that for the moment. Okay, then what I did here was I looked at the overlap. So I said if this value is greater than 0.05, then give me a 1. Now remember, the null hypothesis is true. So how many values should we get that are 1s? Well, we add up this column, and we find that we rejected we failed to reject the null hypothesis 966 times. So we expected in a perfect world for that to be 950. And then we have a confidence interval here of the difference. We ask, remember we had our Goldilocks rule, we have the standard error of the mean, and we're checking to see if they overlap, if the standard errors of the two groups overlap. And they didn't overlap often enough. This test is too liberal. It finds more differences than it should. That should be 952, but 50 also, but it had over 100 false alarms. If we look at the standard deviation, it's too thick, and it said they were too different, 999 times. They didn't overlap, or they overlapped. And then we have our 84% confidence interval. And actually, this number should be exactly the same as this number, and it was close. I don't know, there's some little decimal point somewhere that didn't quite make it. But in a perfect world, we would have expected the confidence intervals not to overlap 950 times, or to overlap 950 times. And it also was a little bit, and that's our type 1. 1000 minus 967 is our type 1 error. Now we do the same thing when group 1, whose underlying population mean is 100, and group 3, it's 120. So now the truth is that there's a 1.25 true effect size. Now how many times do we reject the null hypothesis? Well, the p-value is greater than 0.05 261 times. So we have failed to correctly reject the null hypothesis 261 times. That's our type 2 error. And here we see the same thing. Again, those numbers should be the same. I probably should figure out why those are not exactly the same, but this is an 84% confidence interval. Same thing there. Now let's come over here for a second, and just want to kind of take home this idea of what it means to be a null hypothesis. So what we have when the differences are absolutely, when the underlying population is 0, the null hypothesis is true, then we look to see how many times we reject it. And it started, these numbers should all be positive, because, well, no they shouldn't. This is the mean of the null hypothesis is 0 for the t, and the standard deviation is kind of based on what the t value is. But if we look up in a table, our critical value, instead of 1.96, is 2.26. Absolute value. So here we have minus 2.4. These are all values that are less than the critical value. So if we look on our graph, 2.26 is right here, and out of 1,000 we have a few that are going down here. So 2.26, so we have 1, 2, 3, 5, 9, 11. 11 out of 1,000 values on the left-hand side of the curve are wrong. These are type 1 errors, alpha errors, and they're to the left. We would reject the null hypothesis when we shouldn't. We have a similar thing at the other end, where 2.26, we have 3, 5, 7, 11, 13. So there we have, it's too conservative. And that's over at this end. So when we say that we either go, oops, wrong one. We either, 2.2 is right there, 2.2 is right here. We have this little piece up here and down here. When we say that it's significant, it's because we have all these possibilities of t's piling up at one area or the other. And the probability is of obtaining a t of this value or greater, and I should have added given the null hypothesis is true. So that's our definition of P, and that's another way you can look at it. I think that'll be enough.